Hello, this is checkpoint 5.28. In this checkpoint, they want us to look at the region inside the right circular cylinder with the equation r is equal to 2 sine theta. And bounded below by the plane, xy plane or r theta plane, and above by z is equal to 4 minus y. And they want us to set up a triple integral with the function f of r theta z in cylindrical coordinates. All right, so our function would normally look like when we set up this triple integral, we would be normally looking at this triple integral over the region E of f dv. And when we translate that to cylindrical coordinates, the dv is going to produce an extra r, and so we'll just try to remember that for later. Now let's focus on on the region that we're talking about. On the xy plane, if you remember this sign, r sine theta, it's a circle, it's a circular disk, or circular disk that goes 2 units here, and so this is centered at 0, 1 and has radius of 1, and so that's how it's going to look like in 2 dimensions. But if we're going to look at it in 3 dimensions, our 3-dimensional graph of that would look like this. It's going along the y-axis. So this will create a cylindrical shape going along the z. All right. Now we have another graph involved here, and the other graph involved is z is equal to 4 minus y. So z is equal to 4 minus y. It looks like it's going to be a plane that's going to be running along the x-axis, because the x is not involved, and so it's the plane that's going to be going this way. It looks like it'll end up cutting this cylinder, and so that cut of the cylinder, if you imagine a cylinder going straight up and then you cut it at an angle, that's kind of like what's happening. So let's draw this shape, or the region that we're talking about. And this has radius too, so it doesn't get cut all the way. It'll get cut just up to the surface. So this is going along the plane here, and this is the side of the cylinder. So it'll look something like that. And regardless of how it looks like, we're going to set up our limits of integration. And the way we're going to set up our limits of integration is that we're going to do the z business first. It says here that it's bounded below by the r theta plane, which is 0. Z is equal to 0, and it's bounded above by this 4 minus y. Now, if we're going to go into cylindrical coordinates, we of course will need to change this y into something else. More specifically, this is going to be r sine theta. At least the convention is that it's r sine theta. And so we're going to replace the y with r sine theta when we do the integral. And then from here, we're going to say our radial distance would just go from 0 to whatever this function is. That's 2 sine theta. Now, remember, the other important part to remember is that you get to draw this whole circle from 0, that's pi over 2, and you finish the whole circle at pi. So theta actually goes from 0 to pi, and that's what we have to remember when we do this this type of polar coordinate function. All right, now that we have all the pieces together, we can put this into our integral form, and we have the triple integral of your f of r theta z function, whatever that function is. The dv, remember, becomes an r, and then we're going to integrate with respect to z first, z going from 0 to 4 minus not y but r sine theta, and then our r goes from 0 to 2 sine theta, and then our z, oops, we already did our z, so the last one is theta. The theta goes from 0 to pi. Okay, there is no actual function to compute, so this is the setup, and that's it. Okay, I hope that helps.